Okay, so we want to talk about how to AI power an organization. And so let's start by asking organizations what they want from AI. When we go out there and talk to large companies and businesses, often what we get as far as their vision of what AI can do for them looks something like this. We want you to predict the yield of my crop or diagnose disease from MRI, predict the risk of insuring a property. One thing that's interesting about all of these requests is the fact that the expectation there is about making predictions, making diagnostics, some form of analytics. We want to get something from the data that we have there. And it's understandable. Because the state of AI and the state of, for example, deep learning is all about this magical black box that can reveal patterns in your historical data. And so what is expected from it then is more analytics. But what would they do once they have this analytics? They would buy the correct amount of seeds. They would take appropriate action on the fraudulent transaction. So there's some action, some decisions that these organizations, these businesses are considering to be their own. This is what we will do once the AI reveals what is there. So there's some action that they're considering. But what does this mean? This means lots and lots and lots more insights and charts and things to go through in order for you to make a decision. It's really not quite helping, is it? And so, I believe that insights alone are not enough. We need more. Why are insights alone not enough? Let's look at a few examples. If, for example, our AI kind of says, all right, in 6 months you're going to miss your revenue target. That's something that we would expect our AI to be able to give us with good confidence. What do we do then? Are we going to cut costs? Are we going to sell at a discount? Should we retarget sales, invest in growth? How much of which one of these should we do and where? The AI is not giving us that. That's now upon us. And these decisions are relatively coarse-grained. So the costs are high. What do I do about it? Should I reduce costs across the board or just in a certain division? Should I renegotiate the prices? Should I invest in efficiency? These are all choices that are now up to the decision maker. So the last challenge here with decisions is that decisions are never to optimize just one objective. Decisions are always multi-objective. We want to maximize revenue while maximizing sales, minimizing cost. It's not just one thing that we expect. And multi-objective problems are not very simple. If it were just one objective, it would be quite easy. If we were to bring our cost to zero, we could just fire everyone and shut down. That's zero cost. If we want to maximize our sales, just sell everything for free. These are laughable extremes. But the moment you deviate from these, you're looking for some balance of more than one objective. And it's not an easy problem to solve. And finally, it's not enough for us to just build a deep learning model or any kind of model and throw it over the wall based on historical data, because the world is changing. And because the underlying rules that govern how we would make decisions are actually changing all the time. So a one-shot model building system is not going to be sufficient. And so I think the expectation should be that AI helps us with our decision making in an organization. Let's look at what the state of AI is today when it comes to decision making. Surely, if AI can beat the grandmaster in Go or chess, it must be good at making decisions, right? If AI is able to actually play Flappy Bird as well as we can, it surely can help us with decision making, right? Well, not so fast. We have a few issues. The state-of-the-art in reinforcement learning means we have to actually learn the universe of possibilities. We have to experience the universe of possibilities. All levels of Flappy Bird needs to be experienced. If something weird suddenly happens, the system won't be able to play. If we change something on the system, if we change the rules, if we suddenly say when you flap, you go down versus going up, the system's not going to recover unless you actually teach it everything from scratch. So the state of the art when it comes to decision-making in AI is not quite where we want it to be, simply because it hasn't been applied to decision-making the way we expected. So let's look at how we can actually do that. Let's start with looking at what decisions are. A decision is comprised of this little triangle that I drew here is a good way of modeling a decision. We're in a certain context, and we have some choices, some actions to pick from. And that's the decision. But we don't just randomly pick one of the actions. We pick the actions through a strategy that would optimize the objectives. So that's the way we make decisions. How do we do this? How do we create that strategy? We don't just go out there in the real world and try things. It's costly. So what we do is we create a mental model. If you look at the top left-hand side of this chart, that's our experiences. So we've made experiences, and then we create this mental model in our brains, and then we actually try out different decision strategies against that mental model. This isn't a virtual world in our heads. And then we come up with a better strategy, we go act on it. So given a context, we do something in the real world. That's experience that's added to our historical data. So if we view it that way, we can now look at the various different components. That mental model that I talked about, let's call that a predictor. What that does is it basically says, given a context and an action in that context, what is the outcome going to be? Right? And there may be more than one outcome. But what are the values of those outcomes going to be? And make that prediction based on the historical decisions that you've made in the past. We can actually build this. This is data science. It's actually pretty standard. If you have a database of context actions and associated outcomes, you can create a model based on that using, I don't know, logistic regression or machine learning approaches such as neural networks, backpropagation. It's important to note here that the outcomes that we're talking about might be lagged, and often are. You don't get the outcome immediately. But typically when we look at organizations, in some table somewhere, they've actually got the actual outcomes of the granular decisions that they've made out in the field. And it might be some decision, some outcome that happened 3 months later, 6 months later, but it can still be associated to the context action pair. So if we have that, if we have sufficient data there, we can create a predictor. Then there's what we call the prescriptor. The prescriptor is the strategy. It's basically looking at a context, possibly that we've never seen before, and giving us a prescription for what to do. And it's doing so in order to optimize the outcomes. But then there's this question of how do we create this prescriptor? So how do humans make decisions? This prescriptor is going to be pretty creative. So we need to kind of look at how humans are creative in the way they strategize and make decisions. And the way we make decisions is we have some historical strategy, for example, and we tweak it just a little bit. We make a minor change to it and see if that change actually helped. If it helped, we keep it. If it didn't help, we toss it. And so that's generally our creative process in decision making. For example, the nose cone of the bullet train, the Shinkansen there, that was designed by humans to maximize the aerodynamicity. And they kept making minor changes to it. The problem there, though, was that even though it was very aerodynamic, it made a loud booming sound when it went in or out of a tunnel. So it wasn't sufficient to just do minor tweaks to create this. It needed more creativity. That's the problem we get with hill climbing. The decision algorithm that I just mentioned to you, that is a hill climb. What does that mean? I mean, it's a hill. So just imagine this is a terrain, and we want to find the highest peak. If we have one person, one climber, in other words, just one candidate solution, and we want to find the highest peak, that guy can start taking steps around where they are, and whichever step actually gets them higher towards the optimum is a good move. And so if we continue doing that, we'll find the highest peak. In a terrain that looks like this, yeah, sometimes we might actually be on a hill, but if we restart randomly a couple of times, the chances are we'll find the highest mountain and we'll, go up that. So that is the state of the art today of finding AI-based solutions. It's gradient descent or ascent, depending on how you look at it. And that's what it follows. It's pretty good, but it kind of falls apart when your search space starts looking like this. This is a very deceptive search space, many, many hills. So having one climber trying to do a hill climb is not going to get you too far. Or when the search space is very large, or when the search space is two-dimensional. There's too many dimensions, too many variables, and this here is 3. And, of course, our familiar problem of multi-objectivity. So we're not just scaling one hill. We have to find the balance of more than one optimum. There is a very good way of tackling these sorts of problems, and it's called evolutionary computation. It actually started at the same time, at the dawn of modern computing with Alan Turing. It is a population-based approach, and it allows us both creativity, efficiency, and it can allow for multi-objectivity. And very simple view of it is that rather than using one climber, we parachute in an army of climbers into that terrain and have them start doing a hill climb. But these guys, the ones that aren't really doing too well, we can remove. The ones that are doing better can talk to each other and mix and match their strategies. And for example, you can see a cross-section of that deceptive terrain here, where each dot represents one of those solutions. And what's fascinating about evolutionary computation is that if you're actually on two hills, mixing and matching the characteristics of these candidate solutions that made them better might actually drop you onto a higher hill. And that actually happens quite often. We can tackle very, very large search space, 2 to the 2 to the 70. This is a 70 multiplexer problem. The search space is so large, and there's only one correct solution. It is so large that if you print that number in 8 font characters, it will take light 98 years just to go from one end to the other. That's how unfathomably large the search space is. It's also been shown that very high dimensional problems, such as problems with 1 billion variables, can be tackled with evolutionary computation. So we think that evolution is not just the new deep learning, but it complements deep learning quite well. And we can use it to create these prescriptors. So what do? We actually create a bunch of strategies, multiple candidate strategies. And we run them against the predictor. Remember the predictor that we created using data science. We actually run it against the predictor and say, what if I chose this action in this context? How would that do with my outcome? What if I did this other thing, right? And we gauge how well these prescriptors are doing. And because it's a population-based approach, we are able to very efficiently find the best strategies against our sort of model of the world. It's also multi-objective. So putting it all back together again, we have this approach. It's called evolutionary surrogate-assisted prescription. It's a big name, but it's very much similar to the way I described how we make decisions. So on the top left-hand side is the historical decision-making that goes on in most organizations. It's actually captured. Based on that, using data science, we create a predictor model. And then the prescriptor is evolved against that predictor model. Now, the prescriptor comes out with a prescription in a new context. It says, do this in this context, along with a confidence in that prescription. And often the decision maker, this is an augmented system, the decision maker may or may not decide to go with that decision. Regardless, we capture it. When it goes to the real world, we capture it. And so we go back through the loop. We have more data, and we can decide how to do with the predictions. Let's look at what this looks like. So we create a little model of decision making. So the x-axis is the context, the y-axis is the action. The ground truth, what the world actually looks like if you experience everything, is that kind of little halo, that circle halo in the background. And each point is a decision. Now, let's assume that the best decisions are aligned with the line across on y equals 0. So if you make a decision and your action is 0 all the time, then you're in a good place. This is just a model. So we're going to start this loop that I just talked about. We're going to collect data with experiences in the real world, create a predictor, evolve against the predictor, and then based on the prescriptor that we evolve, we go with the next point. So what you're going to see here is that gradually, the points that we're picking are going to get closer and closer to y equals 0. So that means that these decisions are now more and more optimal. Also of interest is as we're collecting the data, the predictor's view of what reality looks like starts looking more and more like that circle that we talked about. So we're kind of experiencing and learning the world while we're making decisions as well. And the cost is minimized because we're not really going out there and trying stuff in the real world that often. We're only trying stuff once we know it's the right way to do it. So if we look at this other chart here, you can see in the beginning, towards y equals 0, we made a few wild decisions. But after that, most of our decisions are actually quite good and close to optimal. So let's look at some real-world applications of this, starting with Basel. So in collaboration with MIT Media Lab up here in Cambridge, we created a system like this to come up with ways to grow basil in completely controlled environments. Now, humanity's been growing stuff for thousands of years, but nobody knows how to grow things if you take away the context. And so it's a very interesting AI problem. And so what we did is we created a model. The outcomes are multi-objective. We want the plant to be large, so we're measuring the fresh weight of the fully grown plant after 6 to 8 weeks from seedling. And we're also measuring the taste, which has to do with the volatiles in the plant's leaves. And we want to optimize them. And it's multi-objective in the fact that the objectives are not aligned. You know, the larger the plant, the less tasty. So you want to find the best balance. What's amazing is we found that if we shine light, so all the agriculture scientists thought that basil needs to sleep 6 to 8 hours, so darkness 6 to 8 hours every 24 hours. But the system found that if you actually shine light on it for 24/7, it actually thrives. Something that is not possible out in the real world, but the AI was able to find through the same methodology that we just explained. So what about other businesses? I work for a company called Cognizant. At Cognizant, one of the big things that we do is RFPs come in for example, developing or testing software. And we have to decide how to do that. How do we test a particular software? And we have outcomes. Those outcomes are, we want to minimize cost while maximizing speed and maximizing quality. So that's a decision cycle that we can actually AI enable right there. And here's the data set. Just a simplified data set. I don't know if you can see it. It's a little small. But each row here is a decision. And the green is the context, which is basically what's in the RFP. The blue is the test, the actions, basically. Should we use onshore versus offshore? What kind of testing should we do? Should it be agile or not? How long? How much dollars do we put into it? These are all very real questions. And we don't want to rely on guesswork or intuition. We want this to be very data-driven. And then the outcomes. Here's another one. Let me see if I can... let's see. I want to give you a quick demo here. Oh, there you go. Whoa. This is going to be tough. OK, so what you're seeing here is a this is an underwriter. I don't know if you guys can see this. This is an underwriter. And their job is to underwrite the various different properties. That's what they do. It's a very data-oriented decision-making problem. And so they're coming into their dashboard. They have a number of properties listed here. You can see that the system has already given some prescriptions. For example, for this property, it's saying don't even bother. Don't even insure this guy. But this one is insurable. So let's click on this property. There's information about the property. We can see information in more detail. This is the information that the underwriter would actually use to make a decision anyway. And you can see here, we actually have the prescription outcome. So it's saying, yes, insure, and insure at a premium of 80 to 90K, so very prescriptive as far as the number is concerned. And I have this confidence in my prescription. And if you actually take my prescription, you're going to have an outcome of whatever loss ratio measured 3 months out. And so forth. And if the user wants, they can also deviate any time from this and go out and try out other outcomes. There's also an executive dashboard for the boss of all the underwriters here. And he or she can see what's going on and also can change the objectives. There are 3 objectives here, and you can change them, but you can't change all 3. Remember, you can't have your cake and eat it too. You can actually make a change in one, but as you change one, the other 2 are going to change. But the system here is giving you the art of the possible. What is the best if you want the best in one, or you change one of the objectives? OK, so just to wrap up very quickly, why do we need AI-enabled decision-making? Well, decisions are multi-objective, and so it's hard. We do need AI to help us with them. We need a principled way of using historical decision data in order to decide how to do things later, just like we do as humans. So we don't want to rely on guesswork or intuition. We don't want to wait until we have all the data about the universe of possibilities. And so this is a way to do AI-driven data collection, because the prescriptor is telling you, here's the best thing to do next. Go try this out. So this is, in a way, the AI is telling you where to collect data. And that data comes back and helps us improve our models. And as the world changes, we're actually able to keep up with that. And finally, we're reducing costs, because we don't need to go out and try all these strategies against the real world. We can try them against our sort of quote-unquote mental model. And of course, finally, we can play Flappy Bird. We can actually play Flappy Bird using this system. Here's Flappy Bird, and you can see the mental model of the Flappy Bird. You can see these pipes are flying around, and all sorts of weird things are happening because we don't have enough data yet. But we're training against the mental model. We go in, about 60 runs into it, and at least the pipes aren't flying around, and it's getting a little more stable. But after a mere 200 iterations, we actually get a Flappy Bird that does really well, competitive to human behavior. This is only 2,000 runs against the real game. That's kind of comparable to how many times it takes a human to get to this level of proficiency. Whereas using deep Q learning, for example, you have to go through 1 million runs. And so I asked you guys to ask this question: where is the most impactful decision cycle in your organization? And what would it look like if you actually start AI enabling all the decision making in your organization? With that, I'm going to take questions if we have a few minutes. Any questions?
Just going to set up this over here for anybody who wants to ask questions.
I do have one question, actually. So evolutionary algorithms can be efficient at exploring a large space, but you have to have multiple different actors. So although you had a smaller amount of game data, did it take just as much time to train as it would take a deep Q network, or does it take less actual compute time? More data efficient, sure, but is it also more compute efficient, is the question.
Evolutionary computation isn't very compute efficient, but it is massively parallelizable. More so than deep networks, obviously, because you're not working on a single solution and tweaking it. You're working in parallel on a population that can be evaluated separately as well. So in that sense, yes, that's from a compute resource perspective, you can still make it go fast, but you do need more compute resources.
Thanks.
Yeah, good question. Any other questions?
So you talked about looking for correlations between context and actions and actual outcomes in the real world, and using that data set to predict future outcomes. Usually those deep learning or evolutionary machine learning and deep learning algorithms in general requires a lot of data to get to a good accuracy level. And the most usual situations in companies is that we have very few combinations of context, action, and outcomes, maybe a few dozen, few hundred. How do you make it work with algorithms that need large-scale data sets?
Great question. Building that predictor model is not trivial, and it does typically take a lot of data. But the data is not going to be balanced, usually, because the historical data is around points that have worked. So they haven't really explored points that are kind of weird in strange places. But that's still fine. As long as you have good coverage, and to get that, if you don't have sufficient data, you have to do some feature engineering. You have to collapse some of the features, and at least initially, as you're collecting data. But we have bootstrapped systems like this with a few hundred decision points. It can be done, and it's not about building the best predictor model. It's about building, the predictor model that the best predictor model given the data. So it's a different problem. As I said, this is a principled approach in that you want to use whatever data you have. And then also remember, the predictor has to give you a confidence range. So if you actually end up with a context that is very, very different than what you've experienced before and you've built the predictor model before, your confidence range on it is going to be too large. But that's also useful, because when you go to the decision augmentation step, the decision maker can look at it and go, even the AI isn't quite confident in this. I'm going to take a guess and go somewhere else with it. That's how we make it work. I think we're out of time. Okay, thank you very much.